Good afternoon, everyone, and welcome to the tutorial of ODA. After the creation of a component with local periodic approximation, we will calculate here the ODA. This is an overlapping domain analysis. Overlapping domain analysis is an improved version of the local periodic approximation, where local periodic approximation only uses the metacells itself to calculate the full wave calculation. ODA will calculate the full wave calculation with the neighboring metacells, so neighbors are taken into account in the full wave calculation. ODA is slower, but still faster than a full wave calculation on the full meta component, which is often not feasible. So now we change the meta component size to 10 micrometer to have a fast example. Now we'll change the metacell library to a library of pillars. This is a silicon oxide pillar library where the pillars have different radii. This is a nice example for ODA because taking the neighbors into account, we will see that when we have a strong switch from a small to a large radius, there will be a clear influence, while if radii are nicely next to each other, there is no difference between LPA and ODA. Meanwhile, I created a matching target, and now I'm adding the near-field wavefront. We will take an aspheric lens with a focal distance of 20 micrometer at 550 nanometer wavelength. This is chosen because it nicely has a 2-pi phase shift, so all pillars will be used in the component design. So we generate this near-field wavefront. Okay, this is added. And now we'll go for the design. The design itself will still use a local periodic approximation to locate every metacell to an appropriate place on the mid component, because this is a very fast calculation and it can calculate all metacells and then define all positions. Okay, the design is finished. So now we go to analysis. We can here choose between local periodic approximation and overlapping domain analysis. The overlapping domain analysis takes much longer, so you have to be first doing a previous calculation. So we don't find anything here in this list yet, because we have to do this separately. So first of all, we go for local periodic approximation. We change the name LPA, and we select to do all analysis. We do go for the far field wavefront, 10 micrometer at 20 micrometer distance, Fourier wavefront, and then we also have the near field wavefront. So a near field wavefront analysis will now run. Okay, this is run. So we have the phase of the near field wavefront. We see indeed that we have a 2-pi phase shift. We have also a focal area. This is about 1 micrometer. So if we zoom in, you see this is indeed a nice focal spot. Cross section is also correct as expected. So for a simple lens with a simple library, we have a far field wavefront efficiency of 0.78, so 78%, which is also not bad. And this is now the local periodic approximation. So now we go for ODA. We will do a calculation at 0.55 nanometer. We do a low accuracy, just for an example to go quickly through it. So accuracy 1 for the metacells, and then we run through it. So at this moment we're running the overlapping domain analysis. This means that we go through each metacell, take into account the single neighboring metacell as well, do a full RCWA calculation, so full wave calculation, and then only take into account the central part of this full wave calculation. We do this for every metacell and stitch then every local field next to each other. With this new near-field wavefront, then we will be able to calculate a more accurate near-field wavefront, a more accurate far-field wavefront, and a Fourier wavefront as well. So now the overlapping domain analysis is done. So this means that we have an ODA amplitude and we can compare it to the LPA. So we have better to go for phase. So here is LPA phase, ODA phase, and then the difference between LPA and ODA phase. We see here that we have a ring. This ring of errors is because we have there a jump from one radius to another radius. This ODA calculation is now specific for this configuration here of 550 nanometer wavelength. So now we go back to the analysis. We do have now a pre-calculated overlapping domain analysis. Now we go to overlapping domain. We select the pre-calculated version. This is directly filled out, so incident light, outgoing conditions, everything. We go for the same analysis, so far field Fourier, and we do a new analysis. We quickly change the name to ODA and go for a new analysis. So now we'll take the near-field wavefront based on the ODA calculations and we'll use this for the rest of the propagation and the analysis in the far field. So here is the result of the analysis. So now we have a far field analysis based on the ODA. Again, looks still like a focus of 1 micrometer, not the amplitude, but we go for the phase. The phase looks very similar as before, slightly different in the center. And now we'll check the Fourier. We can't really see a lot, but if we look for the efficiency, the far field wavefront efficiency, we can compare it with the LPA from before. So the LPA had a far field wavefront efficiency of 0.783. Here we see it at the left top. And if we go to the ODA, we have a far field wavefront efficiency of about 0.671. So we see clearly that there is a difference. The ODA gives a more accurate result of what we have designed with local periodic approximation before.